Very briefly, I had some questions about equilibrium points, especially for the inverted pendulum problem. So I've replicated here the two differential equations that describe the motion along the z-axis and then for theta double dot. So these are the two differential equations that we get from second-order differential equations that we get from physics. So why is it that our equilibrium point is what it is? Well, as you remember, we defined the state to be x1 equals to z, x2 equals to z dot, x3 equals 0, and x3 equals theta, and x4 equals theta dot. And so if we take the time derivative of x, we get x1 dot equals z dot, x2 dot equals z double dot, x3 dot equals theta dot, and x4 dot equals theta double dot. So the definition of equilibrium is that x dot must be equal to 0. And so now we have to find what is the value of our state variables and our input such that x dot will be equal to 0. So that's how we calculate the equilibrium point. So we're going to do it the following way. First, I'm going to set the time derivative equal to 0 for each of these pieces. And we see that by definition, x1 dot must be equal to 0, and therefore z dot is equal to 0. So we get that just from the definition of x1 dot. We also see that x3 dot must be equal to 0, and again x3 dot equals theta dot. So by definition of equilibrium, those two state values must be equal to 0. So now we take the second order differential equation that we have for z double dot, and we set it equal to 0. So this is going to tell us how we can make x2 dot be equal to 0. And so we're going to get to choose values of f, theta dot, and theta such that z double dot is equal to 0. So it turns out that x2 dot is equal to 0 if f is equal to 0. We know that theta dot is equal to 0 by definition, because again theta dot must be equal to 0 to be at an equilibrium point, because theta dot is equivalent to x3 dot. And for the third term, g cosine theta sine theta, we must have a value of theta equal to 0 here. So if theta is any other value, for example in the second term here, we could have a different value for theta because theta dot is going to be 0. So that's going to allow us to have a 0 for this term regardless of the value for theta. But that's not true here, because cosine of theta is equal to 1, and g is not equal to 0. Therefore, if we have any other value for theta besides 0, we're going to be unstable. We're going to have a non-zero value for x2 dot. And so that's why we must have theta equal to 0 in order to satisfy x2 dot is equal to 0. So that solves it for z double dot, and we have to confirm that these values theta dot equal to 0 and theta equal to 0 and f equal to 0 also constitute an equilibrium point at theta double dot. So here we set x4 dot equal to 0, and we confirm that x4 dot is equal to 0. In order for this to happen, we have to have f is equal to 0, again because a 0 value for theta is going to give us a 1 here, so we need for f to be equal to 0 for this term to be 0. Here we already know that if we choose theta to be 0, that the sine term becomes 0. So this entire term becomes 0 here. That's good news. And again, we've defined that theta is equal to 0, so we lose this term as well. This term is going to be 0. So now x4 dot is equal to 0 if we choose the value of theta equal to 0 and theta dot equals to 0 and f equals to 0. So just to remind yourself, f equals to 0 is the same as u0. So this says that our input value u0 requires us to be 0 in order to meet the equilibrium condition.